Is aerospace test ready for digital transformation? My name is Frank Heidemann, CEO of SAT Germany, and me and my colleague Chris Bakker from Tech180 want to discuss exactly that issue. And from digital transformation in the aerospace industry, just one portion, model-based design and model-based system engineering, and what are the effects of test equipment and testing and validation. So the agenda today will cover a couple things. What is digital transformation in terms of model-based system engineering, and why is it so important? The challenges, and especially what are the benefits we can leverage from model-based system engineering in regards to build testers and provide test environments. And a high-level strategy to prepare test infrastructure and to enable the benefit from these model-based design efforts and workflows all over the life cycle of a test equipment. So to explain the differences in the benefits, I want to just jump into the current design cycle of an aerospace product or an aerospace airframe. So the aerospace industry is probably most regulated and most paper-driven and process-driven industry on the globe, and you all know that, right? We have more paper and more documents than we have probably transistors in an airplane, and we just follow very strict regulates and procedures to trace our requirements from a very high level to a down level. So today we define and specify high level designs. We give these informations to subcontractors and OEMs and tier ones in hundreds of other subsystems in an airplane. Then they begin to develop in a concurrent way all these subsystems, and changing requirements flowing down that workflow, and most of the time coming up again, right? Because some systems changes, and these changing requirements reflect in high level requirements changes, and then it just flows down the whole supply chain again. Then we build we build this product and we do a VAV of our designs, and at the end, if all these components and subsystems get built and put together, we bring them to the Airframer and integrate that into a huge system at integration and system level in the integration rig. And then we manufacture and sustain that. So that means we generate requirements and write hundreds of SOVs. We give these SOVs to our suppliers, and they translate it into data they understand and they can use for their design flows. We duplicate basically the equivalent workflows on all these subsystems, and then change these requirements here and there, and they flow back and go back and forth because they're very changey and very flexible in the design phase. And in a very late design stage, we put all the systems together in an integration rig and power up the complete system and validate the complete system. And if you have problems there or issues at the end of the integration stage, that's obviously the most cost-intensive and time-intensive problems to fix. So with a model-based design approach, that would change dramatically. We could build basically a digital twin of the airplane, even if it's a very raw definition of the model. We can hand that over to all these partners and subcontractors and OEMs and tier one suppliers, and they could really concurrent design against that model on a model base. And they could also reflect and feedback their information of their subsystem in form of a model to the airframer. And the airframer could already in a very early stage do a virtual subsystem integration and a virtual validation of the functional subsystems and the functional airframe in total. And that would over time lead to a very, very stable requirement definition and specification of the aircraft, where already a lot of changes of the requirements are covered, because that very agile process of forward development of a model, feeding that to subsystems, and then integrate the information back into that model and validate that already, leads to a very stable definition of the system. But at the end, nothing is without a price, right? At the end, we always need to build the real products. So there is a day at the end of the virtual system integration that we need to build the products, that we need really the real products to validate and verify, then integrate it into real integration benches, manufacture them and sustain them over a long lifetime. But It would be much more cost efficient. It would be much faster and much more agile in the process, and probably much higher quality, since changes in models and changes of systems, when they make absolutely sense and really make systems better, would not be that not that be a big burden as they are today, where we live on a paper-based system, right? So when we look into a life cycle of a test equipment, and that's probably the same life cycle as a product, we have a product with a system definition and an interface definition, and it includes the signal description, electrical tolerances, system and software performances, avionic bus protocols, all these little tiny portions. And on the other side, on the Airframer side, there's exactly the mirror. The inputs and outputs, they get digested on both sides. And then, from this definition, it flows down to several stages of testing. And these stages are, in the very beginning, hardware validation, then software and system validation. Then we need to do end-of-line and ATP testing. We have on Airframer side a huge efforts of integration and system labs to integrate that component into the complete orchestra of all these other subsystems, depot test systems, and service ground support systems at the end of the process. And any portion and any test of that and any test equipment on the way of the life cycle really contributes to program time and budget, right? And on the other hand, all these several disciplines generate their own knowledge and IP on the way they flowing through the life cycle. So we have special IP for production, for system validation, Airframer side, depot, and service side, and they all just duplicate multi times the effort to sustain them and to develop them. But that's only the view on a component on a subsystem. From Airframer's view out, it is a complete different picture. The Airframer now needs to integrate all these products and all these different subsystems in one system and do integration testing and validation and verification. And that, if we follow that process, would lead to a huge system, a huge integration rate with a huge amount of budget and time. And still having these moving targets, because we have changes from one system to another, that there's an inconsistency and we need to change requirements, and then the whole design flow of that test equipment begins from the beginning. But our customers, and that is obviously so, our customers need more modular systems. They want to integrate subsystems for their own, and then being able on a modular approach and interoperability that they can combine one subsystem, one integration bench for a subsystem with another integration bench of another system. So for example, a primary flight control system on a subsystem integration bench to a secondary flight system on another integration bench. And then in a perfect world, it would be perfect to reuse all that box level product IP, all these informations and know-how built and developed already for the test equipment on a box level and a component level side. And if we could reuse that on an integration lab side, we could get from there. Good. So what is that test system impact? So the whole idea, just to covering that up, is reduce the total cost, the risk, and of course the serial time burden of the just reproducing always the same IP and know-how in the workflow and of the lifetime of the equipment. Making sure that all functional blocks are, tested and ported to different lifecycle testers correctly, and not reinventing all the time the wheel new, and then making sure that all these testers and integration benches can really intercooperate and intercommunicate with each other on a very proper way. So that would be a solution, and that would really reduce cost and time in the development cycle. And how we can make that, this is what Chris Bakker, CEO from Tech180, is now talking about, and I'm happy to hand over to him. Have fun.
Okay, so like Frank said, model-based systems engineering should give us a huge efficiency boost across the board when we're developing complex aerospace products. But it also adds the additional challenge of implementing all of these different pieces of test equipment that really represent the boundary between the virtual domain where we're doing this model-based engineering and the physical domain where we're actually going to connect to the real product when it's built. So the output of that model-based engineering workflow needs to be at least requirements written in some kind of descriptive language that's based on the product interface that describes what needs to be implemented in a test system and how to test the product in that particular phase of the life cycle. So ideally, what we're doing is we're producing the requirements in a standard format that can then feed down to all of the stakeholders, telling them exactly what needs to be met when they build their test equipment. But fundamentally, we're not going to really be changing anything about the overall workflow of the industry, right? You're still going to have multiple different test systems being designed by multiple different stakeholders, each with their own workflow, each with their own software preference. So the model-based engineering workflow really is going to black box the product and produce this interface definition in some kind of format. But the IP on each of the individual testers is really going to be specific to that design, the operating system, the hardware that they're using. And so to get that IP to be portable, you're going to have to implement some kind of restriction on each of those groups that are developing the test equipment to make sure that the model interface standards that they're using would be compatible with any of the IP generated in any one of these test systems. That is going to implement more additional work, more additional cost onto each one of these pieces of test equipment, right? This becomes somewhat of a political problem to get all these stakeholders to adopt the same standards and use the same workflow. And it's not really taking us in the right direction. This process is still going to be more expensive, more time-consuming than it would be without the model-based design workflow itself. So what are we going to do to be able to kind of counteract this effect? Okay, so really what we need to do is design some kind of workflow for generating this test equipment directly from the model-based engineering workflow, but at the same time allowing something to get up and running, right, without getting every single person in the entire industry to adopt the same standards. So I'm going to back up real quick, but before model-based systems engineering, I'm going to go back to model-based design, which is a little bit more basic. Software engineers have been using this for years to develop all of the control software and software stacks that go onto aerospace electronics. And it's got a little bit more of a basic topology. You've got a model of the LRU that's on the airframe. You've got a model of the airframe itself. And you're passing back the engineering unit values between the two to drive a closed loop simulation. And the way you would test this virtual airframe here is that you'd use a test script in a test executive environment to stimulate the airframe model. And then what you do is you look for a response either behaviorally from the airframe model or interrogating the memory of the LRU to see that the software saw the right value. Model-based systems engineering is going to be a little bit more complex. Instead of just passing back the actual engineering unit values between the software for the LRU and the airframe model, what we're going to want to do is actually take the whole system into account. So we're going to want to simulate the actual electrical interface of the product, as well as the actual electrical interface of the airframe, separately from the behavioral models, right? So the interface model for the product is like a wrapper for the behavior in the software that's defined by that product interface document that we had described earlier. And likewise, on the airframe side, now we're simulating the wiring and the sensors and the loads, all the things that the product is driving on the airframe, separately from the behavior. And there's some real advantages to doing this. Number one, you're just going to get a much higher fidelity simulation of the entire airframe. And number two, though, you're going to have these interfaces that can much more readily be substituted with real hardware when it comes time to, say, take out the actual product from this simulation and replace it with a real product connected to a test system that is ultimately driven by those same test scripts in that same airframe behavioral model. So let me show you how that's done. So ideally what we'd like to do is be able to take that airframe interface model out and replace it directly with a piece of test equipment, which means we want to generate the design of that test equipment directly from those signal-based requirements that are the output of your model-based engineering workflow. So Tech180, SET, and NI have partnered to develop an off-the-shelf modular open architecture that allows us to synthesize the system designs directly from those product interface requirements. And using all off-the-shelf modular components, we can rapidly design and assemble this system using an agile, iterative approach that allows us to get at the exact piece of test equipment required for any life cycle phase based solely on those initial signal requirements. So if we have the ability to generate test equipment from those product interface requirements in much the same way as we can generate those models from those product interface requirements, then substituting out the virtual components for real components becomes a pretty simple matter, right? The product models obviously get replaced with the real product. The interface between the product interface and the airframe interface model just becomes your cable harness definition, while the airframe model itself becomes the test system, as we discussed. So that leaves kind of the software that governs the test system. That's going to be different depending on what scope that you're in, what life cycle you're in, right? So if you're talking about, a full closed loop simulation and a validation environment, then you can kind of just leave the software environment intact with the airframe behavioral model connected to the test system in exactly the same way that it would in the actual simulation, right? So that's really just a driver level call to the test system hardware as opposed to just reading and writing values between models. But of course, if you're in like a production environment or an aftermarket environment and all you're doing is sequencing through a series of steps, that airframe behavior model can simply be replaced with the hardware extraction layer of the test executive. So we get rid of that closed loop environment. So that takes care of the hardware piece, which should help us reduce the kind of duplicate effort of reproducing the same hardware system multiple times over the course of the program. But in order to solve the other issue, which is to have multiple different workflows from all these different stakeholders interoperate, we're going to want to structure the software and architecture in a particular way. So instead of connecting the models together natively in any random environment, what we're going to want to do is have the models connect directly to a shared memory interface in every environment. That shouldn't have any impact on performance and is structured pretty much exactly like the programs would be anyway. But it's going to allow us to take the data in that environment and export it to other environments. So here you see that it can be connected to the test executive as well. So the test executive can write directly into the model and stimulate the models in the same environment that they're running in. The principal benefit of this is that when it does come time to substitute those models with the real hardware, we can implement that hardware on a completely different machine while still connecting it to the original software environment. Now that's really important to break that connection, because if we're going to have hardware that we know will meet the requirements given the product interface definition, we're going to want to separate the compatibility and the maintenance and the obsolescence support for that hardware from the original software environment where the models were hosted. And of course, if this is not a closed loop environment and we want to go to simply a sequenced environment for, say, a production test or something like that, again, we can remove the airframe model and replace it directly with a hardware abstraction layer to this test executive. Again, note though that the only driver now that anyone's workflow has to support is this read-write memory interface, as opposed to any specific vendor's hardware. This is going to be hugely beneficial, as now you can support any workflow or software environment from any particular stakeholder and use a single generic memory interface to be able to talk to the I/O subsystem. Plus, you can synthesize that I/O subsystem directly from requirements, regardless of whether or not anybody is using the same model-based system engineering workflow in their own design efforts. Extending that concept, now multiple different workflows from multiple different stakeholders can actually be all combined together and drive one or more I/O system layers directly from the shared memory interface and all completely interoperate with each other without any kind of dependency or pre-planning in order for this to happen, other than the structure of the memory in the first place. Okay, so to tie all these concepts together, we've got a product interface description that's generated by our model system engineering workflow. Now that descriptive language can be used to directly synthesize all of the different test equipment that you need in any particular lifecycle phase, all of which will use the same common modular platform to reduce the cost of development, but also maintenance and obsolescence planning for those test systems. But each one of those test systems can still support the workflow of all the individual stakeholders and have the option to port the IP that's generated in any particular lifecycle phase throughout the entire program, meaning that you can now get different test capability where you need it without going through separate design efforts. This is of particular use for the integration lab folks, because now there's the possibility of specifying to the OEMs that they deliver test equipment using this common system platform, but they can do that now without incurring additional cost and time because their OEM workflows are supported natively and don't need to be modified. And then the Airframer has the option to run their own workflow, again, on the same common system platform. And this is going to give everybody the ability to optionally leverage all of the different things that are already being developed for the product line anyway, to all the other stakeholders within the program. So let's recap what test infrastructure needs to do to be ready for a model-based system engineering workflow. That virtual environment is going to produce standard product interface descriptions that are going to allow parity between the virtual domain and the real domain. And it's going to describe what requirements coverage we're going to need to provide in any test equipment that we generate. The common hardware framework that NI, SET, and Tech180 have developed can implement equivalent requirements coverage at the pin in multiple workflows and software environments. And that's going to allow us to port all of the different functional blocks and IP between the different product development life cycles to get greater efficiency and reduce the cost and time that it takes to execute the program. Okay, so a little dose of reality. It's going to take years for the aerospace industry to roll out model-based systems engineering at scale and see the type of benefits that we're talking about here. It's an evolutionary transformation. And as with any kind of evolution, the difficulty lies in laying the foundations and infrastructure necessary to be successful in the future, while also delivering on the programs that you have to perform on today, right? And so our approach, we believe, has the ability to help make that incremental progress and keep you moving forward in a direction that's getting you closer to the goal of practically rolling out this type of model-based system engineering workflow. Now, the way that we can do that is that we can essentially compile test equipment designs from interface descriptive languages. And whether or not you have something that's producing those descriptive languages right now, Tech180 and SET can synthesize that directly from your requirements. And that's going to save you all sorts of time and money and carve out the budget that you need really to make that transformation. Our systems can be used in many different workflow environments, right? So we don't have huge changeover costs or the need to retrain huge numbers of people in order to adopt this test technology in your next system. And as an individual stakeholder, you can see the benefits and the return on investment from adopting this architecture individually, right? You don't need the entire supply chain to get on board with you in order for you to see the benefits directly. And then the program can see benefits from any combination of stakeholders using this, right? The entire program does not have to follow the same workflow and use the same IP in order for any of the stakeholders to provide value to others. Okay, so what's the bottom line? What we're talking about here is taking the test coverage requirements and the implementation IP to be able to test the product and making it portable with the product itself, right? The problem we're trying to solve here is that we don't want every stakeholder in the entire life cycle of an airframe to be reinventing all of the same work again and again. You're going to want to reuse all of the different articles that are created over the years. Models, test scripts, even the design of test systems should follow the product itself. Now, we want to be able to enable a practical model-based systems engineering environment, right? And that means that those virtual interfaces around product models need to be able to turn into hardware interfaces consistently if you're going to leverage that across the entire life cycle. Now, if you do that, the program can save a huge amount of time and money by eliminating all of that duplicate work and all of that translation work. And that's a real benefit. I mean, who doesn't want to save time and money? Who doesn't want to become more efficient? But what this is really going to do for your company is allow you to leverage that in a way that makes you more effective at serving your customers, delivering airframes, delivering subsystems to airframers. So thank you for attending today. Again, my name is Chris Bakker, CEO of Tech180. If you're looking for more information in the US, please email us at info@tech180.us. And if you're in the EU, please email info@smart-e-tech.de. Thank you again.